Hey everyone, I'm Nick, and welcome to another episode of Parallel C++. So in this episode of the series, we're going to be talking about the reduction clause with OpenMP. So our parallel applications often have different phases, right? So for example, we'll have, maybe a parallel phase where our threads are able to do independent work, and then we'll have some sort of synchronization phase where we might be accumulating some partial results. Now, a great example of this is with something like sum reduction. So with sum reduction, we might split up a vector across multiple different threads, and each thread computes some partial sum. Then in some synchronization phase, right, we add up all those partial sums together to get our final result. Now, a great way that we can do this with OpenMP is by directly using this reduction clause. So that's what we're going to be looking at today. So let's go ahead and get started. And we'll start by opening up our baseline here. So we're going to be looking at a couple different benchmarks implemented with Google Benchmark today. And the first one is just going to be a serial version of this reduction. So we're going to be doing a sum of squares, squaring all the numbers in a vector and then adding them into some final result. So here, right, here's our benchmark called baseline. We start by setting up a random number generator, so random floats between 0 and 1. Then we go ahead and create 2 to the 20 elements inside of some vector called vin here. So we push them back with the std generate in, and then we have our timing loop down here. So in each iteration of this timing loop, we're just going to set some floating point sync variable. So this is where we're going to accumulate our partial results here. So we set this to 0 each iteration. Then we do this sum of squares, right? So we iterate over the num elements inside of our vector, and we do, we square each element and add it to sync here. We have this call to benchmark do not optimize to make sure that sync doesn't get optimized away. Okay, so that's going to be our serial implementation. Let's see how we can implement it in parallel with OpenMP and using this reduction clause. So we'll open up this reduction.cpp, and what we see is that it looks almost identical to our other version here. So we have the exact same setup with this Mersenne twister, random number generator, generating numbers between 0 and 1, 2 to the 20 total elements inside of our vector vin, and then we have our timing loop where each iteration we set sync equal to 0, and then we go ahead and have our loop, right, where we're accumulating these squares, right, our vin elements squared. But above this, right, this is the loop that we want to parallelize here. We want to parallelize this reduction. So here, unsurprisingly, as we've seen in the past, we want to parallelize this for loop. So we start by using pragma OMP parallel for. So this is just specifying that I want to create a group of threads to run this for loop, and I want to split the iterations of this loop right across these different threads. But then after this, we add this reduction clause, right? And we provide an operator and a variable here. So this is saying I want to do, for my reduction, I want to do an add for this variable sync up here, this floating point number. But what exactly does this mean here? So if we look at the right-hand side of the screen, I've got the Lawrence Livermore National Lab OpenMP tutorial up, and specifically I have this section on this reduction clause. So it says that the reduction clause performs a reduction on the variables that appear in its list. So that's just going to be sync in this case. And it says that a private copy for each list variable is created for each thread. And at the end of the reduction variable is applied to all private copies of the shared variable. And that the final result is written to the global shared variable. Now, what exactly does this mean? So as we've seen in the past, right, one thing that we don't want to do is have, tons of synchronization points here. So what we don't want to have happen is say make our updates to sync here be atomic and have every thread fighting over this exact same variable, right? And then we would just have a cache line bouncing around between our different cores, right, trying to access sync. So we don't want to make, our operations with sync atomic and shared across all of our different threads. And we don't want to do something like locking either. We don't want to have to grab a lock just to update sync every single time. That just serializes our work across our different threads. We don't get any benefit of parallelization there. So what we can do instead is give each thread its own private copy of sync. That way each thread can accumulate its part of the vector in private, right, with their own copy of sync. And then all we need to do at the very end is accumulate those partial results here. Right? So we still have to add up the partial results from all of our different threads, but now we only have to say do 8 additions of this or 8 updates to sync here from different threads, rather than, the entire vector length, right? 2 to the 20 elements all trying to update, all going to the exact same piece of memory. So what we're doing here is we're giving each thread a local copy of sync to update, and then we're just going to, at the very end, accumulate these partial results. Okay, so let's see how the performance compares between this the serial and this parallel implementation. So we'll go ahead and compile both of these. So we'll start with baseline. So here we're using O3 optimizations and then linking against libpthread and libbenchmark for Google Benchmark. And then we'll compile a reduction with the exact same flags, with the exception that we also need to turn on OpenMP with this -f OpenMP. So we can go ahead and run baseline first, and we see that it takes somewhere in the order of 2,300 microseconds to run. And then we see that with our reduction benchmark, where we parallelized it, it's a whole heck of a lot faster, right? Somewhere between, maybe 5 times, a little less than 5 times faster here. So 490 microseconds versus 2,300 microseconds. So a big speed up improvement, right? And that should be somewhat obvious, right? We have a very parallel problem here. The only synchronization we really need to do is this accumulation of our partial results at the very end. Okay, so let's go ahead and look at the underlying assembly and see how that differs between the two. So we'll go ahead and do perf record with 0 baseline first, and then perf report so we can see the assembly of this tight inner loop. And we can see that the code is pretty intuitive. So each iteration of the loop, we're just going to be loading a floating point number into xmem0. Then we're doing our multiplication, right, with that register with itself. So this is just squaring a number. And then we do this add, right, of, xmem1 and xmem0. So this is just going to be us accumulating, partial results each iteration of the loop. Then, right, of course, we have our loop counter here. So we're moving over 4 bytes each time. And then we're checking to see if we're done each iteration of the loop, right? So we're just comparing against our total number of iterations here. So that's going to be our serial implementation. Now let's look at our parallel implementation here. So we'll do perf record on 1 reduction, right? That's where we're using this OpenMP reduction clause. And we can go ahead and do perf report here. And if we go ahead and take a look at baseline here and our tight inner loop, we see that it looks just about the same here. So each thread, right, with its private copy of that sync variable is doing roughly the same work, just on a chunk of the vector or part of the vector. So it loads a value into xmem0, squares it by multiplying it with itself, and then accumulates its local partial results here. And then each iteration of the loop, it compares against the number of iterations it's supposed to run. Okay. Now, what we see is something slightly different after we get out of this tight inner loop where we're doing this, partial sum accumulation, right, for, a private chunk of the vector. We see that after this, we actually have a small section of our code dedicated to this accumulation of those global partial results. So our results across our different threads. And you can see that this is done using this compare and exchange loop down here. So if we go ahead and take a look at this, we have, this loop down here that's right after our hot inner loop, where on each iteration of the loop, we try and do this lock, compare, and exchange with our partial result here. So we're accumulating our results across our different threads. If we're able to, successfully do this compare and exchange, right, we just exit out. Otherwise, we load the most recent value of our global sync variable. We jump back up, we try to add our partial result again, and then we try to do this compare and exchange again. So this is just a loop that's used to combine those partial results at the end of our parallel execution, or when each thread finishes their chunk of this vector. Okay, so that's going to go ahead and do it for today. It's a brief introduction to this reduction clause with OpenMP. So this is really, a really nice thing and a way that makes us more productive, right? If we go ahead and take a look at our code again, you can see that we didn't have to write this custom, reduction across our different threads ourselves, right? We could just specify, hey, I want the automatic parallelization to take care of this partial sum reduction across our different threads for us, right? We didn't have to manually manage local copies of sync for each thread, and then, accumulate those into our global copy here, right? OpenMP took care of that for us. Now, below the video, I'll make sure to link this LLNL tutorial again, and specifically this section on the reduction clause. And as always, you can find this or any of my other examples at github.com/coffeebeforearch, right in this parallel CPP repository. But that's going to go ahead and do it for today. As always, I'm Nick, and I hope you have a nice day.